Hello students. So today we will continue NCERT chapter 8, which is aldehyde, ketones and carboxylic acids. Today is the theory part 10. Section which we are going to cover today is section 8.9.2 to 8.9.3. This is the disclaimer. So what is the objective of today's lecture? After attending this lecture, you will be able to understand the topics which we are going to cover today. So today we will describe the chemical reactions of carboxylic acids and we will explain the mechanism of few selected reactions of carboxylic acids. Now for your reference, I have mapped the NCERT section which we will cover today. So we will cover section 8.9.2, which is reactions involving cleavage of COH bond, and we will see section 8.9.3, which is reactions involving COOH group. And finally, we will summarize whatever we have studied in today's lecture. So let's begin with reactions involving cleavage of COH bond. So today we are going to see some important reactions involving carboxylic acids. And specifically, we will focus on the reactions that involve the cleavage of carbon and oxygen bond, that is COH bond. So carboxylic acids, they can undergo the following reactions which involve the cleavage of COH bond. So one by one, we are going to see all these reactions. First, we will discuss the formation of anhydrides. So anhydrides are formed when two carboxylic acid molecules react losing a molecule of water. Okay, so two carboxylic acids react and they lose of water. That results in the formation of anhydride. Next, we will study about esterification. So this is a reaction where a carboxylic acid reacts with an alcohol to form an ester and water. So if I talk about the use of ester, so ester are widely used in fragrances and flavorings. Next, we will see the reactions with phosphorus pentachloride, which is PCl5, phosphorus trichloride, which is PCl3, and thionyl chloride, which is SOCl2. So these reagents, they are used to convert carboxylic acids into acyl chlorides, which are highly reactive. And finally, we will see the reaction with ammonia. So when carboxylic acids react with ammonia, they form amides. So one by one, we are going to see all of these reactions as well as their mechanisms. First, we will study with the formation of anhydrides. So first, we need to look at the reagents that are needed for the formation of anhydrides from carboxylic acids. Okay. So carboxylic acids, they can form anhydrides when they are heated with specific reagents. So one of the reagent used is mineral acid. Okay, that is this H2SO4. So H2SO4 helps in the dehydration process, which is crucial for forming the anhydrides. So if I talk about the role of this acid over here, it is to facilitate the removal of water. Another reagent that can be used is phosphorus pentaoxide, which is P2O5. So this compound is a powerful dehydrating agent, means it can effectively remove water from carboxylic acids to form anhydrides. Okay, so here one thing you need to notice is that how different reagents, they can achieve more or less similar outcomes. Now look at the process. Here you will see that a water molecule is lost from two carboxylic acid molecules to form an anhydride. Okay, so if you see over here, you have two molecules of carboxylic acid. This is one molecule and this is another molecule. So dehydration process is happening. That means water is being removed. So one hydroxyl group from this acid and one hydrogen from this acid is removed. So H2O is removed. So in the presence of mineral acids or phosphorus acids, okay, in the presence of heat, you will see that you will form an anhydride and water is being released. Okay, so by dehydration of carboxylic acid, you get anhydrides. Now, if we look at a specific example, we will see over here we have two molecules of ethanoic acid. This is ethanoic acid. It undergoes dehydration in the presence of heat and mineral acids or P2O5 to give anhydride. So here it is ethanoic anhydride. Okay, so that is water is removed from carboxylic acid to give ethanoic anhydride, which is an anhydride. Okay, so this is the formation of anhydride. So carboxylic acids, they form anhydrides when heated with H2SO4 or P2O5. Okay. Now we will see about the esterification. So esterification is important because it allows you to create esters. Okay, and esters, they have wide range of applications from fragrances to plastics. So carboxylic acid, they react with alcohol or phenol to form esters. So if you look at this particular reaction, here you will see you have a carboxylic acid. When it reacts with alcohol or phenol, in the presence of an acid, this is catalyzed by an acid, you get an ester, water. So you can see that this reaction is a reversible reaction and it is catalyzed by an acid. So this shows the transformation of carboxylic acid and alcohol into an ester and water. So if we discuss the role of catalyst in this reaction, so mineral acids like H2SO4 or hydrochloric acid, they act as a catalyst. So they help to speed up the reaction without getting consumed in the process. So it makes the esterification more efficient. So if you look at this example, here you have benzoic acid. This benzoic acid reacts with methanol, which is CH3OH. In the presence of H2SO4, you get methyl benzoate, which is an ester. Okay, so this reaction is an esterification reaction which proceeds through a nucleophilic attack of alcohol on this carbonyl carbon, and which is followed by the elimination of water. So this proceeds through a nucleophilic acyl substitution. It is an example of nucleophilic acyl substitution. Okay, so when you react carboxylic acids with alcohols or phenols, you get an ester. Now we will see the mechanism, that how is this reaction happening. So this is the overall mechanism of esterification. One by one we will discuss all the steps. So first step, it is the carbonyl oxygen of the carboxyl group is protonated. So this is the carbonyl oxygen of the carboxylic group. It is protonated. So what happens? This protonation, it activates the carbonyl group, which makes it more susceptible to nucleophilic attack. So if you'll see over here, this oxygen gets protonated and now it is more susceptible to a nucleophilic attack. In step 2, what happens? The lone pair of electrons on alcohol. So if you see, this is OH, the oxygen of this alcohol group, it has lone pairs. It attacks this carbonyl carbon. Okay, and it forms an tetrahedral intermediate, which is a temporary structure in this reaction. So when this alcohol attacks on this carbonyl carbon, you get this tetrahedral intermediate. Next step is that the hydroxyl group, the hydroxyl, which is the OH group of the intermediate, it undergoes proton transfer. Okay, so you will see that this hydroxyl group of OH, it undergoes the proton transfer. This converts it into a better leaving group, which is OH2 plus. Okay, so now this we know that OH is not a better leaving group, so a proton transfer takes place, and you see now you have OH2, which is a better leaving group. So a hydroxyl group converts into a better leaving OH2 by proton transfer. Now in the next step, this OH2 group is eliminated as a neutral water molecule. Okay, so this will be eliminated and you will see you get a protonated ester. Okay, so this elimination, it helps you form an protonated ester. And in the final step, this protonated ester, it loses a proton to give you ester as a product. So this deprotonation, it stabilizes the ester and completes the reaction. So this results in a stable ester molecule, which is often used in applications like perfumes and flavorings. So this is the process of esterification, that how from carboxylic acid, by reacting it with alcohols or phenols, you get an ester. Now, next we are going to study the reactions with PCl5, PCl3 and SOCl2. So if you see over here, then carboxylic acid, which is represented as RCOOH, they are converted into acid chloride, which is RCOCl. So this transformation, it can be achieved using reagents like PCl5, which is phosphorus pentachloride, or PCl3, which is phosphorus trichloride, and thionyl chloride, which is SOCl2. So each of these reagents, they have their own pathway as well as their byproducts. So if you look at this reaction with phosphorus pentachloride, which is PCl5, so this reagent, it reacts with carboxylic acid, okay, to give acid chloride, which is RCOCl. So this reaction is represented as this carboxylic acid. When they reacts with PCl5, they give RCOCl plus PCOCl3 and HCl. So if you notice the byproduct, which includes phosphorus oxychloride, which is POCl3, and hydrochloric acid, which is HCl3. So this reaction is quite efficient for converting carboxylic acids to acid chlorides. Next, we have the reaction with phosphorus trichloride, which is PCl3. So in this reaction, 3 molecules of carboxylic acid, they react with 1 molecule of PCl3 to produce 3 molecules of acid chloride and phosphorus acid as byproduct. So see over here, you get H3PO3, which is the phosphorus acid as byproduct. So this method is useful when you are dealing with larger quantities of carboxylic acids. Next, we will discuss the reaction with thionyl chloride, which is SOCl2. So this reagent is particularly favored because it produces gaseous byproducts. Okay, so this reaction with SOCl2 is favored because if you see over here, the byproducts which you get is SO2 and HCl. Okay, so they are gaseous byproducts which can be easily removed from the reaction mixture. So when you react carboxylic acid with SOCl2, you get acid chloride and these byproducts. So this makes the purification of acid chloride much simpler. That is why this is particularly favored. Okay, so what is happening in this reaction? Important aspect is that there is the replacement of this hydroxyl group in the carboxylic acid with a chlorine atom. So if you see, this OH group is replaced by this chlorine atom. So this substitution is what transforms the carboxylic acids into acid chlorides. Now, as I told you that among the reagents which we have discussed, thionyl chloride is often preferred. Okay, so reason is its gaseous byproducts, which is SO2 and HCl. So this makes the purification of acid chloride much easier. Okay, so reason is given that gaseous byproducts, they make product purification much easier. Okay, so we discussed that how carboxylic acids can be converted into acid chlorides using PCl5, PCl3 and SOCl2. So each reagent has its own advantage, but thionyl chloride is preferred because of the ease of product purification. Now, we are going to see the mechanism of the reaction of carboxylic acids with SOCl2. So now in step 1, the sulfur atom of SOCl2 is attacked by the carboxylic acid, which forms this unstable intermediate. So if you see over here, this sulfur is quite electrophilic because it is connected by two highly electronegative chlorine atoms. Okay, so in first step, this sulfur, it is attacked by the carboxylic acid and forms this unstable intermediate. Okay, so sulfur over here acts as an electrophile, which is attracting the nucleophilic oxygen from this carboxylic acid. Okay, so if you'll see over here, this oxygen has a positive charge. Now this chlorine takes up this hydrogen and you get an unstable intermediate. Now in step 2, the intermediate formed in first step gets protonated. So in first step, you will see this is the unstable intermediate. Now this unstable intermediate is getting protonated. So now this protonation, it makes the intermediate more reactive, okay, and allows it to interact with the chloride ion. So now this has become more reactive and a chlorine atom attacks this intermediate, okay, attacks this. So this intermediate now forms a tetrahedral intermediate. Okay, so now this is forming a tetrahedral intermediate, which then finally collapse to give the final product, which is an acid chloride and SO2 and HCl. Okay, so finally you will see that this intermediate is unstable and will finally collapse. That is, this chlorine will take up this hydrogen. There will be a carbon double bond oxygen, and this group SO2 will leave from here. So you will get acid chloride, HCl and SO2. Okay, so this is the mechanism that how this reaction is happening. Now we are going to see the reaction with ammonia. Okay, so this reaction, it leads to the formation of amides. So if you look at this reaction, when a carboxylic acid, it reacts with ammonia, okay, it initially gives you an ammonium salt. Okay, so when this carboxylic acid is reacting with ammonia, it gives you an ammonium salt. And this ammonium salt, upon heating, loses water and transforms into an amide. Okay, so if you look at this reaction, you have a carboxylic acid, then reacted with ammonia, it gives you ammonium carboxylate. And upon heating, this loses a water molecule and it transforms into an amide. If you look at this example over here, you see that acetic acid, it reacts with ammonia, okay, and it gives you ammonium acetate. And this ammonium acetate on strong heating gives you acetoamide, which is an amide. So if we further continue, we will see the mechanism of this reaction. So in step 1, you see that ammonia over here acts as a base rather than a nucleophile. Okay, so carboxylic acid, they have this acidic proton. So ammonia will abstract this acidic hydrogen, okay, or H plus ion from this compound, and it forms an ammonium salt. Okay, so this ammonia will act as a base. It will take up this acidic hydrogen and it will give you an ammonium salt. Now in step 2, we heat this ammonium salt at high temperature. So this ammonium salt loses a water molecule, and this dehydration leads to the formation of an amide. So finally, if you see over here, you get amide. Now we will see the reaction of phthalic acid with ammonia. Okay, so this is an interesting reaction because it involves a transformation from a dicarboxylic acid to an amide. So if we look over here, then phthalic acid, okay, it is a benzene ring with two carboxylic groups in the ortho position. Okay, so this reacts with ammonia to form ammonium phthalate. Next, when we heat the ammonium salts, so ammonium phthalate, it undergoes condensation, that is loss of water. So each of this COO minus NOH NH4 plus group, they loses water to form an amide group, which is phthalimide. Okay, so finally you will see that from this you finally get this product when this CO minus NH4 plus loses the water molecules. Okay, so finally you get phthalimide. Now finally, when we are doing the strong heating, so this phthalimide, it converts into thalliumide. Okay, so from here, if you look at this particular reaction, then NH2 condenses with the adjacent C double bond O of other CONH2 group. Okay, so finally, if you see, there will be elimination of NH3 group, and this forms a cyclic 5-membered cyclic imide. Okay, so if you see over here, final product which you are seeing over here is a 5-membered cyclic imide. Okay, so if you look at this cyclic compound, so this acyclic compound with 2 carbonyl groups and 1 imide nitrogen. Okay, so this is the final product which you get of this reaction of phthalic acid, which is a dicarboxylic acid, and when you react it with ammonia. First, you get phthalimide, and when you further strong heat this phthalimide, you get finally this 5-membered cyclic imide. So if you look at this particular compound, okay, then you have 2 carbonyl over here and you have 1 imide nitrogen. So it is a stable compound and it is often used in the synthesis of other chemicals. Now we will see that carboxylic acids, they undergo following reactions which involve COOH group. Okay, so first we will discuss reduction. So reduction involves the conversion of carboxylic acid group into an alcohol. Okay, so if I give you a real example, then it is the conversion of acetic acid to ethanol. Next, we have the decarboxylation. So this reaction involves the removal of the carboxyl group as CO2, effectively shortening the carbon chain of the molecule. Okay, so one by one we will discuss each of these reactions. So first, carboxylic acids, they can be reduced to primary alcohols using specific reagents. First reagent which we use is lithium aluminium hydride, which is LiAlH4. So this is a powerful reducing agent and can effectively convert carboxylic acids into primary alcohol. Okay, so if you see over here, LiAlH4 is quite reactive and it must be handled with care. Next, which we can use is diborane, which is B2H6. So this is an alternative to LiAlH4 and is also effective in reducing carboxylic acids to primary alcohols. Okay. So if you look at this particular reaction, you have a carboxylic acid which is represented as RCOOH when it is treated with lithium aluminium hydride in ether or with B2H6, which is diborane. and which is further followed by the hydrolysis. It is reduced to primary alcohol, which is RCH2OH. Okay. So diborane, it is often preferred over LiLH4 for the reduction of carboxylic acid. Now, why is it so? This is because this B2H6, which is diborane, it doesn't reduce other functional groups like esters, nitro groups, or halo groups. Okay, so it does not reduce other groups. This selectively can be advantage when you are working with complex molecules that contains multiple functional groups. Okay, so it will not reduce these groups like ester, nitro, and halo. It will particularly reduce this carboxylic group. Now it is important to note over here that this sodium borohydride, which is NaBH4, it does not reduce the carboxyl group. Okay, so this is crucial because NaBH4 is a milder reducing agent when we compare it with LiLH4 and B2H6. So it is because being a milder reagent, it does not reduce these carboxyl group. Okay, it is often used for reducing aldehydes and ketones, but not the carboxylic acids. Next, we are going to see the concept of decarboxylation. So, decarboxylation, this specifically refers to the removal of CO2 from an organic molecule. That is the removal of carbon dioxide. So, decarboxylation of carboxylic acids, they take place during following reactions. First one is heating with soda lime. So, this is a common laboratory method which is used to remove the carboxyl group from the carboxylic acids and which results in the formation of hydrocarbons. Okay, so this is a very straightforward and efficient way to achieve decarboxylation. Next is Kolbe electrolysis. So this technique involves the electrochemical decarboxylation of carboxylic acids to produce hydrocarbons. Okay, so one by one we will discuss this. First, we are seeing heating with soda lime. So first, let us start by defining what is soda lime. So it is a mixture of sodium hydroxide, which is NaOH, and calcium oxide, which is CaO. Okay, and this is present in the ratio 3:1. So this combination is crucial because it facilitates the removal of carbon dioxide from the carboxylic acids. Okay, so if you look over here, CaO, which is calcium oxide, it acts as a drying agent. So the mixture stays solid and it is easy to handle. So first, carboxylic acid is converted to sodium salt. And on heating with soda lime, the COONA group is removed as Na2CO3. So the organic, which is the R part, it gets converted into RH, which is an alkane. So that is why it is called as decarboxylation reaction. That is the loss of COOH as CO2. Okay. So from the loss of carbon dioxide, it results in the formation of hydrocarbons. So the product is always one carbon less than the original acid. Okay, so you'll always see that this will be one carbon less. So if you look at this particular reaction, you have sodium carboxylate, which is RCOONA. And when it reacts with soda lime, which is a mixture of NaOH and CaO, it produces an alkane and sodium carbonate, which is Na2CO3. Okay, so if you look at this product, this is always one carbon chain short. Okay, if you look here, this is, if you compare this sodium carboxylate and this alkane, this is one carbon short. So look at this particular example. You have sodium ethonate, okay, which is CH3COONA. When it reacts with NaOH and CaO, and it is heated to produce methane, which is an alkane, and you get Na2CO3 with its sodium carbonate. Okay, so you can see here that how a acid, which is a simple carboxylic acid, okay, it simple carboxylic acid derivative, it can be converted into a hydrocarbon. And you can clearly see that here it is CH3COONA. Here there are two carbons and here there is only one carbon. So this process gives always one carbon is short or one carbon is lost. So this significance of this reaction lies in its ability to decrease the carbon chain length. Okay, so each time you apply this reaction, the carbon chain shortens by one carbon atom. So if you want to prepare a lower alkane from a higher acid, then this is quite a useful method. Next, we are going to see it with Kolbe electrolysis. Okay, so this is a method where we use electrolysis to transform carboxylic acid into hydrocarbons. So if you see, during this process, we perform electrolysis on aqueous solution of alkali metal, salts of carboxylic acids. And this results in the formation of hydrocarbons. Now, an interesting aspect of this reaction is that the hydrocarbons formed contain twice the number of carbon atoms as the alkyl group in the original carboxylic acid. So this doubling effect is quite crucial because it allows us to predict the structure of this resulting hydrocarbon. Okay, so the hydrocarbon always contains twice number of carbon atoms which is present in the alkyl group of carboxylic acid. If you look at this general reaction, we are starting with two molecules of sodium carboxylate, and when you further do the electrolysis, through electrolysis we get an alkane and sodium hydroxide, carbon dioxide and hydrogen gas. So you will see over here that this hydrocarbon, it contains twice the number of carbon atoms present in the alkyl groups of this carboxylic acid. Okay, so this sees the transformation of a carboxylate to a hydrocarbon. So if you look at this example, you can see you have two molecules of sodium acetate. Through electrolysis, you are getting an alkane, which is an ethane, and you are getting sodium hydroxide, NaOH, carbon dioxide, and H2 gas. Okay, so the important thing is that it contains twice the number of carbon atoms. Now, we will summarize whatever we have studied in today's class. So today we discussed the key reactions of carboxylic acids involving the cleavage of COH bond. So first, we will look at the formation of anhydrides. So when two carboxylic acid molecules react, they form anhydride by losing a water. Okay, so if this is carboxylic acid, when they lose a water molecule, they form anhydride. So this reaction is driven by heat. Okay, so this is the formation of anhydrides from the two molecules of carboxylic acids. Now, if I talk about anhydrides, then they are quite useful in organic synthesis, which serves as an intermediate in the production of other compounds. Next, we have esterification. It is a reaction between a carboxylic acid and an alcohol or phenol. So this process forms an ester and water. Okay, and it is catalyzed by an acid. So esters, they are commonly found in fragrances and flavors, which makes this reaction significant in both industrial and natural processes. Next, we discussed about the formation of acid chlorides. So carboxylic acid reacts with PCl5, PCl3 or SOCl2 to form acid chlorides. So these are highly reactive compounds which is used in the acylation reactions. So if we look at this particular reaction, in this reaction, phosphorus pentachloride, which is PCl5, it reacts with carboxylic acid and is converted into acid chloride, and the byproduct you get is POCl3 and HCl. So it is a straightforward method to obtain acid chlorides from carboxylic acids. Next, we are using phosphorus trichloride, which is PCl3. So 3 molecules of carboxylic acid reacts with this PCl3 to give you 3 molecules of acid chloride. Along, you get a byproduct, which is H3PO3. Okay? So this method is efficient for large scale synthesis of acid chlorides. Next, we discuss the reaction with thionyl chloride, which is SOCl2. So this is particularly advantageous because the byproducts you get is sulfur dioxide and hydrogen chloride. So these byproducts, they can be easily removed from the reaction mixture. So this makes the process cleaner and more efficient. Next, we discuss the reaction with ammonia. So carboxylic acid reacts with ammonia to form ammonium carboxylate, which upon heating loses a water molecule or loses water to form an amide. So amides, they are quite important in the production of polymers and pharmaceuticals. Okay. Next, we discussed the reduction. So in this reaction, a carboxylic acid is reduced to primary alcohol. See, this is a primary alcohol because the carbon to which your OH group is attached is further connected by one carbon atom only. So this is a primary alcohol. And this is achieved using reagents like lithium aluminum hydride, which is LiAlH4, or diborane, which is B2H6. Okay. So in this, we discussed that B2H6 is more efficiently used for this process. And we also saw that sodium borohydride, which is NaBH4, is not used for reducing carboxylic acid, because it is quite a milder agent. Okay, so for that it is basically used for aldehyde purpose. Next, we saw decarboxylation. So this process involves the removal of carboxyl group from a carboxylic acid, which results in the formation of an alkane. So first we saw decarboxylation, in which we saw sodium carboxylate, which is RCONA. It is heated with sodium hydroxide and CaO, which is soda lime, and it produces an alkane and sodium carbonate. So this is useful for simplifying complex molecules by removing CO2. Okay, and this always gives you an alkane which is one carbon short. Finally, we saw the electrolysis of sodium carboxylate. So when two molecules of sodium carboxylate react with water during electrolysis, they form an alkane. And the byproducts you get is sodium hydroxide, carbon dioxide, and H2 gas. So this method is quite useful for generating alkanes from carboxylic acids in a controlled manner. So if you see over here, this always doubles the number of carbon atoms. Okay, so this is, we discussed two methods, that is, one is reduction and one is decarboxylation. Okay, so thank you students for attending this lecture. I hope you understood the topics which we discussed. I hope you all have a nice day. Thank you.